Good afternoon, ladies and gentlemen. I am very happy to introduce Valeria de Paiva, who is a researcher working on logic, mathematics, and computer science since a while. I can say that this history started when Valeria finished a bachelor in mathematics in Rio de Janeiro, and then a master in mathematics in algebra, also in the Puc-Rio de Janeiro. And then Valeria moved to University of Cambridge, where she finished a PhD in mathematics and computer science in a very interesting topic, deontic logic. And okay, the history continues. After that, Valeria contributes to areas like category and computer science, logic, always relating topics from mathematics, logic, type theory, proof theory, rewriting, and what is most interesting from all that is that Valeria always had some contact with industrial parties. She is currently working in the in some institute in California, and for several years worked on with industrial partners in California, and affiliated to universities like nowadays the PUC from Rio de Janeiro, the Birmingham University, and also the Cambridge University. I can say that the history from such a successful researcher, Brazilian researcher, started after a very interesting history in mathematics in the previous century. I have to say that Valeria was a result from some other supervisors, famoso supervisors. Alonso Church finished the supervise from Alan Turing in the University of Princeton in 1938. After that, Alan Turing supervised Robin Gandy in 1953. And then, that was in Cambridge University. And then Robin Gandy supervised Martin Holland in Oxford University in 1975. And finally, Martin Hyland supervised Valeria de Paiva in 1988. It's a very it's fantastic for people who work in this branch between computer science and logic, fundamentals of mathematics, foundation of mathematics, and computer science. I am very proud to give the word to Valeria de Paiva, and we are proud to having such a significant person in this plenary. Please, Valeria.
Well, thank you so much, Mauricio, for this lovely introduction, and I'm very pleased to be here, very proud to be talking to you today. Thank you so much. Can we go for the slides now, guys? Let me see if I can go for the enter the full screen. So I hope everyone is seeing my screen, and I hope you all hearing me properly. If there is a problem, please complain to the guys. And as Mauricio was saying, I have a kind of a slightly different career from most traditional mathematicians. And I think I want to talk a little bit about it to you guys today. And my title is Categorical Semantics for Explicit Substitutions. So my thesis was very much in pure category theory in the Department of Pure Mathematics and Mathematical Statistics in Cambridge. But since then, I've been working, as Mauricio also mentioned, thanks very much for the lovely introduction. I've been working on lots of different industrial research outfits, and I'm now working for the Topos Institute, which is a very recent institute that just opened in 2021 in Berkeley. But I'm going to be talking to you guys about some very old work today. So I wanted to start by thanking Dani for the invitation for this talk. Thanks, Dani. And that's us in all of us, or some of us, in one of our meetings about women in logic. And I also want to thank Jacqueline Mesquita for the invitation, because I think that's it is very nice to be talking to people of a slightly larger audience. So I want to talk both to mathematicians and to the theoretical computer scientists that my talk was originally part of. And because the Topos Institute is a different sort of outfit, I thought you might enjoy kind of hearing about our goals. So our goal is a world where the systems that surround us benefit us all, and we want to shape technology for public benefit by advancing sciences of connection and integration. So I reckon that talking to you in this summer school in the Department of Mathematics on a session on theoretical computer science is very much part of this idea of advancing the sciences of connection and integration. And I want to talk about split substitutions, and I want to talk about abstract machines. And these are things that some of you have been hearing quite a bit about. And I want to explain that my perspective is an applied perspective. This is Pierre-Louis Courion, who actually just won a big prize of the French Academy of Sciences, so the French Academy of Science Grand Prize to 2020. And mostly my work that I will be describing here kind of stems from his ideas that theoretical computer science has to pay attention to pure mathematics. And that's the kind of, I hope that makes the other mathematicians more interested in what I have to say today. So being a little bit more precise, I'm going to be talking about the explicit substitutions linear abstract machine. And this kind of builds up from work that was happening at the beginning of the decade. So actually, two decades ago, 20 years ago. So that comes from Ike Ritter, who is a fellow colleague in the University of Birmingham. And he did a PhD in Cambridge as well on categorical combinators for the calculus of constructions in 1992. And as Mauricio was explaining, I actually did my PhD in Cambridge in the maths department, not the computer lab, on models of linear logic and dialectical categories, which actually come from Kurt Gödel. So they have a very illustrious pedigree. And I did my PhD on this dialectical categories and kind of linear lambda calculus. And we put the two together, the two kinds of PhDs together in a single project that we called Categorical Abstract Machines for Linear Functional Programming. And and we submitted that as a project to EPCRC, which is the English CNPq or the English NSF, and we got 3 years funding. And And then you're going to say, well, Valeria, you know, why 20 years later you're talking about this stuff? And I am actually talking about this stuff for several reasons. But the first one is that I have lots of friends in Brasilia who work on explicit substitutions, and I'm forever being mean to them and asking them why they don't think about this stuff that I'm talking about today. And so I want to try to make the connection between my work and their work. And as people who do mathematics for a living know, making connections between deep subjects can sometimes be very hard, because you know you have to kind of learn a new vocabulary to interact with people, and so one of my reasons for giving this talk was actually to kind of try to tell them where we go differently. But another reason is more fashion driven. As I'm saying in this slide, we had a collection of works. We have only 2 journal papers that we kind of submitted, but we had more than 10 papers submitted to conferences, some seriously good conferences. We had a master's thesis. We had 3 international workshops, and we had all this work that actually didn't go very far after the project finished. And it didn't go very far for another collection of reasons, for the fact that I moved to California, and that meant that I couldn't carry on as easily as I was having my work in Birmingham, because I changed subject when I moved here, because I started working for Xerox PARC and I started doing work on AI, and but also because the field itself moved in a somewhat unpredictable to me direction. And 20 years later, things might be ripe again for working on that. So this is bits from Twitter, one already very old in 2016, where people were saying, I mean, someone was giving a talk on linear types for the language Rust, which is a new language of Mozilla that's now getting independent from Mozilla. And more recently still, the project for adding linear types to Haskell has been accepted in 2018, and they're still doing it. So this is my personal motivation for trying to talk about that. So as I was saying, one of my motivations is to talk to my friends in Brasilia who are doing work on that. But my other motivation is actually to see how these things can be developed 20 years later, and see if it is true, the old saying that from academia to industry, you take at least 15 years, sometimes more like 20 years, because, you know, if so, then it is time for our work on that to come in. And then you might say, particularly the more mathematics, I mean, the people who are in the TCS session, probably not, they know all about what explicit substitutions are. But for people that are more mathematicians, they might say, categorical models for what? And what are categorical models, right? And I will explain in a minute what categorical models are and why I think they are very important. But for what is for explicit substitutions, which are one of the things that I keep repeating to my mathematician friends, that computer science is an extremely nice area to find new sorts of problems. Because in computer science, as the quotation here says, lambda calculi are said to have explicit substitutions if they pay special attention to the formalization of the process of substitution. This is in contrast to the standard lambda calculus, where substitutions are performed by beta reductions in an implicit manner. So, you pass it to the meta level and say, well, someone else, please do the substitution. What I know is that a substitution will happen here. And so the traditional wisdom on lambda calculus and the big books, and this was discussed this morning on some of the talks in the TCS session, the explicit substitutions, kind of making them part of the calculus that we are dealing with. So bringing them down from the meta language to the object language that we study. This is a kind of a process that actually brings lots of new mathematical problems that are worth our attention. And one of the things that happened with this subject of explicit substitutions is that there's been a huge number of published calculi of explicit substitutions in the literature, and kind of some people think, well, this is not good. If you have that many of those things and we can't tell which one we should be using, then maybe it's all a bad idea altogether. And of course, we don't think so, but I want to suggest to you that mathematics, kind of traditional mathematics, can bring some intuitions to bear. And I say that we should do that because syntactic calculi, there are plenty of them, but the models are much rarer. And I think actually categorical models, like I'm going to describe, I only know about the ones that I'm talking about here. So in some ways, this is putting the cat amongst the pigeons, because lots of people will disagree with some of my premises. But I hope it's a cat among the pigeons, a bit more like to the left than to the right. The cat there is kind of an old cat that's kind of trying to be friendly to the pigeons instead of trying to eat them. So what we will not see in this talk is some of the main subjects that we've heard in Benimiano's talk or in Jamie Gabai's talk earlier or in Sandra Alves' talk earlier in the session. And so I'm not going to talk about intersection types. I'm not going to talk about evaluation strategies. I'm not going to talk about dynamic types. I'm not going to talk about patterns or proof nets or nominal syntax or geometry of interaction. And I'm certainly not talking about lambda calculus cost models. But I am kind of willing to discuss these things if you want later on. So why categorical semantics, and what are categorical semantics? Categorical semantics comes about fairly early on as far as computer science is concerned. You can see the dates on my slides, 1963, 1965, and the lambda calculus is much earlier than that. And Claudia Nalon was talking a little bit about the beginning of the last century and how things were kind of a little bit complicated for mathematicians because they didn't have kind of clear notions of algorithms or clear definitions of what's computation about. So it's a very old thing for computer scientists, but I was very kind of happy to hear, I think, Cecilia Salgado talk in one of the plenaries that 5 or 10 years ago, kind of very recently. And I said, oh, yes, that's the thing. In mathematics, 10 years ago, or even 20 years ago, it's not a very old stuff that you should just throw away and not think about. It is worth thinking. And some of the mathematical theories that consolidate in they take a while to kind of so that we actually understand what's going on. So the Curry-Howard correspondence, as I was saying, kind of started in the 60s or perhaps even earlier, if you think about, you could even try to find ancestors for that in Sean Finkel in 1908, or the Lambda, or Churchill with the Lambda calculus in 32 or something like that. But it's still being developed in a ways, and the most important idea that I want you to take from this talk, if nothing else, is this idea that the kind of framework we search for is a framework that connects pure mathematics in the shape of certain classes of categories to pure logic in the shape of natural deduction or sequent calculus systems, to kind of pure systems of programming language in the shape of prototypical languages like the Lambda calculus, which is the top of the triangle. So this triangle is what we actually want to understand. I mean, we do understand that version, the propositional version, but we want to understand much more complicated versions of that, and we want to understand it for different logical systems that different computer scientists and different mathematicians want to think about. And each one of us can work in one of the vertices of this triangle, but we actually work on the vertices of this triangle knowing that the other vertices are there, and that there are kind of very strong correspondences between the vertices. So my whole point in this talk is mathematics as a source of intuition. And I say that a syntactic calculus worth of our attention will have a categorical semantics. And that's a little bit of an article of faith, but I will stick to it. And in today's talk, I want to talk about showing that for a version of intuitionistic propositional logic, IPL, and for a version of intuitionistic linear logic, ILL, but that works for CS4 box as well. And we kind of intend, I mean, it works for the calculus of constructions and works for other more sophisticated type systems. So I kind of wanted to kind of go very briefly over the side that I think the other mathematicians won't know much about, which is the side of very superficially talking about functional languages. So the idea of a functional language is that you want to program, to think of programs as mathematical functions that transform inputs and outputs, and that this will work on inductively defined data structures like lists, trees, arrays, and stuff like that. And the important bit here is that you want to think about no side effects, and that means that you can employ traditional mathematical reasoning and substitute equals for equals. And that will give you a kind of a class of language that people use for specific things in computing, particularly for things like the ones that Claudia was describing on her talk. So doing theorem proving and proof assistance, and but also kind of to a large extent for proofs and verification of software. So I have some very old language there, but there is some newer ones that I should have added, like CakeML and the linear Haskell that I mentioned that's still being developed, and there's Agda and IDRIS, and there's many other languages that are considered functional language. And this language usually have a strong type checking that can detect errors already at compile time. And you know, computer scientists are just a bunch of people who kind of just like to discuss this forever. You know, which, I mean, they have lists of the 20 most used language that all the going on all the time. They have lots of people kind of, they have language wars when people kind of choose one over the other. But you know, from the point of view of using mathematical tools, it's clear that the functional languages would be better for us for using your mathematical intuition. So what is this prototypical language that we are going to be dealing with, which is a kind of a very kernel of computation? We will have some types. So we have some G for ground types, and you should think about that as booleans or natural numbers or tables or whatever, arrays, whatever you want to think about, that you're going to think of floats or double floats, whatever. The things that you're going to think as your main values, the things that you're going to be computing with. And you have, and that's because I'm restricting myself to very easy setup. You only have functions from this ground types from a type to a type. And then you have terms, which are variable terms, lambda abstraction, and function application. And then you have and then judgments. You have judgments to explain when the terms are well formed. So you have this assignments of variables to given types. So your x1 is a boolean and your x2 is a natural number, for instance. And when you kind of create your terms, you deduce that a term M is of type A in the context of assigning variables x1 to xn to types A1 to AN in this context gamma. And you only have this 1, 2, 3 rules. The first one says that, you know, if you define your x of being a type A, you can deduce the x of type A. If you using gamma and using an x of type A, you can deduce that M has type B, then you can abstract over the x and get a function of type A to B by using lambda x dot M. And you can apply terms to terms. So if you have an M of type A arrows B and an N of type A, you can get Mn of type B. And this, you know, this is very basic computing, but it's also very basic logic. And you kind of recognize immediately that what you're talking about is just doing implication introduction and doing implication elimination, or kind of applying a function to its argument. And the fact that you can then obtain a Turing-complete language by just adding recursively defined functions via kind of some syntactic sugar, let rec, it's quite impressive. So you kind of inductively define data structures and define functions using let rec, and you get a full Turing-complete language, meaning a language that calculates everything that the von Neumann architecture allows us to compute. And computation is done just using one simple beta reduction idea. This idea that if you have a function lambda x m, you apply it to n, then what you do is you substitute the n for the x in the m. So this looks totally simple, right? But the substitution is the éminence grise here. It's the big villain in some ways, because it brings with it all sorts of difficulties. And what explicit substitutions really do is to kind of invent ways of making this éminence grise show up in the calculus that we're dealing with itself. So we kind of, as I was saying, implementing beta reduction efficiently is very hard. The traditional solution is to create an environment where we store the bindings for terms to variables separately. And then we kind of create the notion of an explicit substitution, which we apply to terms. So you have a modified beta reduction that stores your substitution in the environment and then rewrite the substitutions to create new rewrite rules to eliminate substitutions properly. So that's the new rewrite rules. And the question here is which new rewrite rules you need to have. And that's what Maurice was referring to, as saying that I work with rewriting theories like lots of other people in around us do too, like Mauricio himself, Flávio, Daniel Ventura, lots of friends in Brazil work with this idea that we have rewrite rules to eliminate substitutions, and we want to find the best systems for this rewrite rules. And so, as I was saying, this trick of transforming something that used to be in the meta level into something that it is in the object level, and then kind of creating logical rules for this rewriting. This is the reason for explicit substitutions, and that's where we want to use our mathematical intuitions. So, as mentioned, there's a large number of calculus, and I think I kind of only managed to get to the end of Benemiano's talk this morning, but I think he was talking about old style and new style explicit substitutions, and I think I'm talking about the old style 1991 ones, and but these are, I claim, more appropriate for people who are kind of thinking about it more mathematically, or at least mathematically in the sense of the Curry-Howard, because the lambda sigma calculus of Abadi, Kurian, and Levy, we have notions of substitutions and terms, and we want to describe the substitutions as using rules that look like logical rules, because we are actually thinking of them as a bit of logic, that it's just the logic of dealing with assigning of variables to terms and substituting variables for other variables and variables for other terms. So the main operations that I have here are the operation that if I have a substitution f, this one just invents a new substitution, but if I have a substitution f, I can always add to it. That's the parallel composition of substitutions. I can add to it a substitution that takes x, makes x be substituted by t, and I have this ability to kind of, if I have two substitutions, f that transforms gammas into deltas and a g that transforms deltas into a psi, I can do one and the other, and that's another substitution. And the important thing is how we kind of cash out the substitution. So I have a substitution f and a term t, and I apply the substitution f to the term t, and it's this application that we want to make as clean mathematically possible as possible, as clean mathematically possible as we can. I'm not going to talk about, I have here an attempt at saying a little bit about how we all agree that all explicit substitutions decompose the implicit substitutions into atomic steps to allow for a better understanding of the execution of models. I think we all agree that we use, we incorporate the substitution operators in the object language and transform equalities into a set of rewriting rules. So far, so good. Some people think that composition of substitutions is not necessary. Because I'm thinking of category theory, I say yes, they are absolutely necessary. So Delia Kessner, summing up her work on explicit substitutions in 2009, kind of says that they allow for more sophisticated interactions, and I agree. But I think that they are not something. It's not a cherry on the top. You can't get out of it. I think she would agree too that they are to a certain level essential. There's lots of things that are not essential, and Benemiano also again talks about some of them, like whether the De Broglie notation needs to be used or not, whether you talk about unary or n-ary substitutions, or whether you want to use combinators of terms, or whether you want to use directory strings or whatever. These things, there are lots of things that can be used in different ways, and we don't want to think about them, at least not for this talk. But one of the main things that happens is that we discovered in 1995 by Paul and André Méliès, showed our counterexamples showing that one of the results that we can't have if we just use the calculus that I showed before, and that the lambda sigma calculus of Abadi, Corian, and Levy, is that we cannot have strong normalization of open terms. And Delia says that there are several ways to avoid the counterexample, and yes, we will have our own version here, which passes by kind of just choosing some strategies. But I don't want to talk about that. I want to talk about the categorical semantics. So let's try to look at it as mathematics, and let's think about if we're looking at it as a problem in mathematics, what can we say? Well, we need to discover which term constructors we should require, and we have been talking about it already in our previous slide. We have to discover which equations we should require, and that is harder. And you have to discover this for different logics if we can do it for the ones that we are kind of originally interested in. As I was saying, my methodology will be to extend the Curry-Howard correspondence, and this is a very different application of category theory, because I'm applying category theory as a syntax debugging tool. And I'm going to talk about something called the internal language of the category to give term constructs and to give an equation of theory. And because I need to have some notion of conservativity of the theories that I'm talking about. So, we created the lambda. I mean, we know what the lambda calculus does. It kind of computes functions, right? And we know that we decided to add the split substitutions to it to facilitate our life, to make our implementations run better. So we think that whenever you have a categorical model of the split substitutions, we have to have a model of the underlying lambda calculus contained inside the model of the split substitutions. And then, if you know a little bit more about it, you know that normally what we do is to think about models of typed lambda calculus, to think about types like x to think about an assignment of variables x and a and y and b as being isomorphic to a context of the type z of type product a cross b. And what we're going to be doing is we're going to be kind of trying to relax the isomorphism condition here. So, and as I was saying, I'm actually trying to bring back to you intuitions from mathematics. And, in particular, I wanted to mention, my models are fibrations. We are not elliptic fibrations, but, I was kind of impressed that in Cecilia Salgado's plenary, she had this picture, which is very much the kind of picture that I tend to use to talk about how I think of this indexing of terms in the lambda calculus. It's this idea that, you have a projection and you look at what's happening on the base category, in this, I'm going to be calling the base category the B there for base, and I will say that the substitutions are going to be happening on the X of her drawing, and I want to bear with me because I'm not going to be able to give you any kind of good indications of why this is so, but I think I'm thinking about my stuff as a little bit like the example that Carolina had on her plenary, where, as you can see, the thing that lives over the basis is very complicated. It can be, I mean, she thinks that P2 is easy, but, you know, can be very complicated. Whereas when you, but what is important for us is actually having this idea that, that we have an X on top and we have the basis B on the bottom, and we actually think about vibrations that on the basis, in their cases, lots of other interesting things happen. In my cases, things are easy. They are syntax. They are X of type A1, Y of type A2, and things like that. It's what happens in the basis. They are just kind of telling you which variables are of which types and how you can substitute when you can substitute one variable for another. Whereas in the top of the surface, lots of things happen. So finally, we get into the main part of the talk, which is the categorical semantics. And now you know, I'm sorry, you'll have to kind of put up with some things that I hope at least the guys in the TCS session will understand. But you know, mathematicians are kind of forgiven if they don't know these things. So I'm going to think about this modeling as done in 3 levels. I have, as I was saying, the base B is a Cartesian category, and by that I mean that I'm thinking about adding substitutions. So I have a T of sorry. I want to think about extending contexts as just being a Cartesian operation. So if I have an X of type A1 and I have a Y of type A2 and I put the two together, then I'm thinking of it as being a real Cartesian product to begin with. So this parallel composition of substitutions is, to begin with, a Cartesian structure. And I will think about the terms as being this thing on the top, thinking about that beautiful surface that Carolina has. We're thinking about that as a funny surface, and each fiber over each point over each fiber, we will have judgments like the one on the terms here, which says that T is of type B if X is of type A, and the other assignments in gamma happen. And reindexing, meaning redoing the substitution, it will be a functor from from the fiber over delta to the fiber over gamma. So to begin with, people were thinking about modeling substitution calculus as an index, as a functor from C op to cat, which, you know, is what we call an index category, and which is a very bad name, right? Because, you know, it's not a category per se. It's just a collection. It has the base and the surface and the vibration and the projection. And it's not really very good for what I want to do next, which is to relax the condition, relax the structure, the Cartesian instruction that I have on the context. So what's wrong with the index categories from the point of view of substitutions? Well, not everything is wrong with the index categories. Some of them are good things. So the index categories induce exactly the lambda sigma equations that I didn't show you before, but I did say that they were part of the Abadie, Kurian, and Levy calculus. So, you know, if you have an empty empty substitutions followed by a substitution H, then you have H, and you have H followed by an empty, you have H again. So identity works the way it should. The applying an empty substitution to the T gives you exactly T, which you get out from the functoriality of the D that we just kind of try to describe. And you have a few other things like kind of composition. Composition is sequential composition is associative, right? The fourth equation here, and you can get easily soundness and completeness of this calculi, but we have no syntax for forming substitutions from the terms, and we don't have. And we have this notion that that if we have a category there, I need to have judgments of the shape gamma followed by x in A gives us x in A. And while this is very sensible as traditional logic, it's not very sensible as linear logic. Because in linear logic, you cannot simply take the projection there. In linear logic, the different bits of a context, they are not related necessarily by real products. They tend to be related by tensor products. And so we kind of invent this notion of a context handling category, which removes the identities by changing the codomain of my main structure to set, and by adding two natural transformations that do what we want them to do. So they do the substitutions and they define the terms. And this this context handling category can be either Cartesian or linear. So, you know, I'm giving myself an extra dimension, a bit of elbow room to think about non-classical logic. So if I was thinking just about intuitionistic logics, or even classical logic, I could think about Cartesian handling categories only. But I want to think about a linear one, because as I was saying, I'm always thinking in the back of my mind that I want to go for different logics in the long run. And then unary dilemma comes to play its normal role here, which in this case is to kind of provide a natural isomorphism between these two natural transformations, which make terms become morphisms and morphisms become terms. And then, you know, I get this notion of a context handling category, which models simply the behavior of the explicit substitutions. So, you know, we can model their formation and the application to terms. But to do my calculations, I actually need real lambda terms. So I need real types, and I really need to have the implication on the example, and I need to have some product. So I need to have these guys here as parts of my types. You know, you cannot calculate by just doing substitutions all the time. It's just, you know, it's not just a game of giving variable types and passing them around for doing nothing. We need to have at least the implication between the guys and possibly more the products. So I give you some given types A and B. We kind of need you to always be able to create these other types, and then we need to kind of have isomorphisms natural in gamma that transform the terms from that have a context gamma A to B into terms that from the context gamma give you an arrow B. So this is just kind of modeling the basis of the lambda calculus itself without products. And this is, oh, and there's a missing closing thing here, but you know, these are, this is the essential of the lambda calculus, and this is the second thing that we normally think about in lambda calculus, and we get naturality equations coming out of the category theory. But we have a little bit of a, you know, you could call it a model collapse, that A product B is isomorphic to X in A and Y in B, which, you know, is good for intuitionistic logic, not so good for linear. So for linear things, I want to keep as much as the structures as I had before. So I will have a type of linear implications, and I will have a type of tensor products of variables, kind of X and A and Y and B becoming just a tensor. And that will give me isomorphisms in my term categories, and that will kind of give us some sort of a natural isomorphism between these guys. And, you know, I didn't talk much about which equations we should have and how to orient them, but all the time I'm using the category theory to design, to guide the design of the calculus. And then we have the hardest time, which is to kind of put the two together, the normal intuitionistic type things that people knew before, and the linear things that we constructed because we are interested in linear explicit substitutions. And we have to, so you know, we create a notion of E categories that model calculi with traditional types like so. We create L categories which model calculi with linear implications and linear conjunctions, linear unity like that. And we use the traditional idea that I actually was part of my thesis, kind of.
Valeria, we have
yes.
We have 9 minutes to finish. Then, if you want to let some time for questions. Okay.
Thank you very much. I'm kind of, believe it or not, I'm getting there. I mean, you can see 27 to 31, we're getting there. Let me try to kind of speed up though. So you do have the way of putting the two together, which was created a while back. And, oops, now this. And you have, you know, lots of categorical theorems, because you have to prove that the structures that we created work as they should. So you have 3 theorems for the E categories, 3 theorems for the L categories, and 2 theorems for putting the L categories and the E categories together. And these theorems are kind of very paradigmatic, because, you know, the first one says that the model that we invented does what it's supposed to do. So, you know, the E category contains an underlying CCC, and each CCC extends to an E category in an isomorphic way. We can show soundness of the logical system, and then we show completeness of the logical system, and you do the same for the L categories, and you put the two together using Barber's calculi drill if you want. And we get to the conclusion. So index categories are inherently nonlinear, so we use pre-sheaves. So kind of it's the bit of substituting cat for sets. Explicit substitutions are tricky to model extensionally, because you have to have the equivalence to the underlying lambda calculus, and we actually do that via our kind of our theorems. We have 3 theorems and 2 theorems, so the number 1 and 4 are kind of doing exactly that. So our models reflect that difficulty by taking isomorphisms seriously, and we do get a Curry-Howard correspondence justifying our calculus. And we could do some other stuff within this framework of Curry-Howard. So more conclusions. Maybe it's more important to have models for explicit substitutions than for the linear explicit substitutions. I think, I mean, that's a good discussion to have in the questions. Another interesting thing to do with this kind of framework is to think about which vibrations, which ones are the interesting ones. Can the mathematicians really give us more than a passing clue on that? Thinking about Sandra Alves' calculus, can we model patterns with our vibrations too? Other logics, I didn't mention much, but I mentioned in that slide with all the old things, we can do some model logics, and I know Claudia is very interested in several model logics. I don't know which ones I can do. And I think I want to thank here, just to end here, thanking people for inviting me to this workshop, and to say that I'm actually very happy to try to discuss that with the friends who are doing work on explicit substitutions in Brazil and other places, and you know, and to say that another thing that warms my heart is to see that we just had this meeting, another summer school, not in Brasilia, but in Espírito Santo, where they had more than 200 people doing category theory. So, so thank you very much. I'll stop here.
Okay, thank you very much, Valeria, for the nice and didactic presentation. I think it is interesting to see now whether we have some questions from the audience. Let's see. Well, I see many people saying hi, good afternoon, and things like that. Some people clap. Okay, let's see whether someone elaborates the question. And then before they write something else, I suppose Daniel Ventura will have some question specific on explicit substitution and the calculus, something like that. Flavio perhaps also. But well, one point that I think is very important in this kind of research area is in order to have some significance is to think about implementations.
Yeah.
For instance,
it's all implemented, right? My stuff is all implemented.
Yeah. That is crucial. No, when I think about explicit substitutions, I worked for on that topic for more than 10 years. The most successful paper, perhaps, is the one from Abadi, Cardelli-Curien. You forgot to say Cardelli was also involved in this paper from 1991. And Gopalan Nagatur, who implemented with Del Miller the sigma prologue. And when I think about nominal syntax and nominal logic, the most successful work in this area has to do with computation implementations. One work is the work from Manuel Fernandez and Jane Gabay on nominal rewriting, and from the point of view of language, the alpha prologue from Jane Chen, and so on. No, it's very important to connect the foundations with the applications. Then, what do you think about implementing all this stuff with your explicit substitution categorical approach?
Well, it's been implemented, right? Ritter implemented in 1994 the calculus of constructions, which is much more complicated than the one that I'm talking about, because I'm talking about just the simply typed lambda calculus and the linear lambda calculus. And we do have the implementation of the linear lambda calculus too. The linear lambda calculus doesn't do as much as we wanted it to do, because we had very high hopes for it in terms of satisfying single pointer property and stuff like that. And yes, it did not do that. So that's one of the reasons why we stopped working it for a while. As I said, I don't want to discuss much about the nominal logic stuff, because I think the concerns there are a little bit orthogonal. So I think nominal languages are very interesting per se, but I don't think the explicit substitutions need to pay so much attention to that, because I agree with Beniaminiano, who was saying that actually alpha conversion does not make a huge difference for us, because we can deal with stuff either using terms or using de Broglie indices. And actually, when we implement, we use de Broglie indices because kind of people think that that's easier to deal with, and everyone that I know kind of uses de Broglie indices. So I totally agree with you that that is very important to think about the implementation, because that is the reason why we start the whole project, right? But the difference is that I was saying you need a big group where some people are going to be good implementers and some people are going to be thinking about the more mathematical side of it. And I'm kind of definitely on the more mathematical side of it. So, if you ask me to tell you what is the cost model of our calculi or anything like that, I have no idea. And I don't really know how the implementation should go.
I try to ask some questions very quickly, no? The first one is from Daniel Enantes. Valeria. Okay, this is screen. It's in the screen. Can you see? Yes.
I can see it. What's your opinion regarding the difficulty in allocating this kind of mathematics in a department in Brazilian university? Well, you see, Daniele, I thought it was very hard, right? I thought it was really very difficult to kind of work this line between mathematics and computer science. But, seeing this 210 guys in this workshop that I just posted about, the last picture, I was saying, well, I got it wrong. It's fine. People are doing it, right? Because, that's a big number of people. And I understand, Danny, your concern, and I agree that it's not a triviality. It's a difficulty for everyone everywhere, right? Kind of, because you don't want the CS guys to swallow the mathematicians, but you also don't want the mathematicians to say that what you're doing in CS is not mathematical enough for them, that it's second-rate mathematics, because it isn't. It is actually very interesting and different kind of mathematics. So yeah, I think you're right. It's a difficult tightrope to walk.
We have another question. I don't know whether
I can see some questions here. Let me kind of. You mentioned it takes time for theoretical concepts to reach industry. Have social. Sorry, you want to go for which one? I think Mauricio, you're the one who choose.
Okay.
Which one? We go this one.
Okay. Yes. Answer the one from Yuri, and then I will send another question from Daniel Ventura, and another one from Flavio de Mora by email. Right?
Okay. So quickly. Mention takes time. Have social media smartphones push for the development of new theoretical logical computation steps? Yes, right, lots. not exactly the kind of theoretical logic computations concepts that I wanted them to push, but yes, kind of, all the stuff on deep learning and stuff, it kind of, we are behind. We need to kind of catch up with the guys, and I don't have any magic wands for that. Sorry.
Okay, this one is from Daniel Ventura.
The question raised in conclusion about model of yes in the linear case. Well, I think we do have. I think I do have a version of explicit substitutions for the linear lambda calculus that it is good, and that satisfies the categorical models without any problems. The question is whether the implementations of that are as good as the theory. And you see, what happens to linear logic in general in the last 25 years is that people did not apply linear logic wholesale. They picked up little bits of it and put in different systems. So, you have, as I was saying, you have these linear types in Haskell, which are just one type, not the whole language moved around it. You have lots of link. The Microsoft thing uses one bit of linear. Some of the linear ideas have been used, but linear logic as a whole has not been used, Danielle. So I think the point is, maybe we really don't want to have the whole of linear logic implemented. Maybe we actually really want to implement bits of it, kind of, particularly the bits that have complexity, implicit computational complexity more under control. I don't know very well, but I think, I think we have the tools, so kind of we need to do more calculations.
Okay.
That's a very good question, Flavio. Yes. I think it is possible to see the flaws in the design of the calculi from the categorical side. I mean, I think what's difficult is to decide whether the flaw is worth the trouble or not, right? Because you see, the category theory gives you some guidance, but it's not a do that. It's kind of more like, if you do this, you get this and that extra properties, and they are more natural. And so, it will depend very much on what you personally think as natural and what you want to use your stuff for. So I think, I'm kind of giving this talk because I want actually to kind of get the proposal of categorical explicit substitutions back on the table, because it's been taken off. People like Benimiano, who kind of are the forefront of the stuff, the maximum that they think about, I mean, if you remember his six things, 6 properties that explicit substitution calculus should have, the main thing for him, the further that he went, was to say the notational semantics. And I want more than the notational semantics. Even Dennis Scott himself is going for categorical semantics now. So kind of, I don't want to restrict myself to domains only. I think we should go for the categorical domain itself. And I think you're kind of going to get stuff out of it. You don't have to go for the version that I have. I think, you can go for the version that you like best, so long as you kind of pay attention to the categorical things that they are implying. You will see which kind of category theory you are getting with, because we know we're going to relax things, either relaxing things in the semantics or in the syntax. So which kind of relaxation you want to do and why? That is the questions that I think are worth pursuing now.
Okay.
Thank you.
I would like to thank you for the nice presentation and for your time. in name of our group, in name of las siglas, mi grupo de teoría de la computación, with how you motivated the women to work in this bridge between computer science and mathematics. Okay?
Thank you. Many thanks, many thanks. Thanks a lot.
Okay.
It's gonna stop now.